Hello, this is Mr. Collier, and today we're doing some optimization problems using calculus. Okay, so optimization is finding the best possible solution. This involves finding a minimum or maximum using calculus depending on the context. Okay, so in this example, we got a cylindrical dog food can. Show that h equals this here expression. Okay, this is very common type of thing to do, and this is what we're going to do. Basically, you have a formula for the area, the surface area, and you have a formula for the volume. You use both of them, and one of them is going to give you an equation like this that we can substitute the other equation to find a minimum or a maximum. So always start with what's given. We're given 600. That's the volume, so we're going to start with that formula. So volume equals pi r squared h for a cylinder, which is in the formula booklet. So 600. Now x is the radius here, so equals pi times x squared times h. It's a show that question, so we're not using that information. This is like our answer. We're going to simplify the expression until we get this. Okay, we're almost there. This is just dividing both sides by pi x squared. So we need to show these steps, and hopefully it gets you the result from the show that question, and it does. H equals 600 over pi x squared. Okay, so even if you weren't able to do that, you can still start in number B because they give you the result from the previous section. Okay, so let's go ahead and look at the next section. Find an expression for the curved surface area. That's in the formula booklet, the IB formula booklet. The curved surface is 2 pi RH. Okay, so R, in this case, the radius is x in the cylinder. H is our expression from before, so it's 600 over pi x squared. And let's simplify that. The pi's cancel. This x cancels with one of those. So 2 times 600 is 1200. So you have 1200 over x, which equals 1200x to the power of negative 1. I'm just going to write like that because I know I'm going to do some calculus in a second. Hence, write down the expression for the total surface area. So that means also, so we just found the area of the curved surface. We also need to find the area of the two circles. There's a circle on the top and a circle on the bottom. So the total area, let's write it as A. I should probably use a separate letter for before. It's called S. What the total area is 1200 x to the power negative 1 plus the two circles, and the circle is pi r squared. So that's an expression for the total area, including the circles on the top and the bottom. Okay, C, differentiate. So we can call it dA dx, or A prime, equals, the derivative is negative 1200 x to the power of negative 2 reduced to exponent by 1. And this is going to be plus 4 pi x. Okay, so that is the derivative. Part E, calculate the minimum surface area. Now if it said hence, then you have to use the derivative. Okay, so if it said hence, you have to use the derivative. But it does not say hence here, so you can actually just type in the area equation directly and find the minimum surface area. Okay, so let's go to apps function and type that in. 1200 over x squared over x. Let's write it as a fraction. You can write it as an exponent as well. Plus 2 pi times x squared. Okay, when we plot, well, I can't see it all. You can zoom in with your fingers on the actual thing, but I'm going to bump this up. I know it's probably going to go up to the thousands. Let's see. So I've increased my maximum y value, and then you always get a graph like this. Ignore the stuff on the negative side because we can't have negative numbers for radius anyway. So this is our minimum value over here somewhere. Let's do menu, function, extremum, and it gives you the minimum is 4.57. Okay, let me draw the sketch. 4.57, comma 393. Okay, so that means when the radius is 4.57, we have a minimum surface area of 393. So the answer is 393 centimeters. So it's a surface area, so centimeters squared. Okay, now if it said hence here, then you have to use the derivative. Okay, now the derivative at the minimums and maximums is 0. So let's call this method 2. And you'd have to do this if it said hence, or if it said use the derivative. So we can set 0 equal to negative 1200 x power negative 2 plus 4 pi x. Okay, so we can do that. Let's do that on the calculator. Okay, let's go to function and delete this one. And type in negative 1200 over x squared plus 4 pi x. Plot. Now this is the graph of the derivative. If I go to menu, function, intersection of root, okay, that's where the derivative equals 0, and you get 4.57, which is the same as we got in the original graph. So this gives you x equals 4.57. If you want to find the y value, or the area, in this case, you do 1200 times 4.57 to the power negative 1 plus 2 pi times 4.57 squared. Okay, but you want to use the exact value from your calculator, which you cannot copy actually, so you probably want to actually write that down. Function root, you want more digits to be more accurate. 078 1497 34. Okay, so when you type into your calculator, you should get about 393, the same way we did it the other way. Okay, so to sum up, if it says hence, you have to do it with the derivative. If not, you can just graph the original function and get it directly. Okay, so let's look at the next example. So we got a rectangular field. Okay, the diagram shows a rectangular field of area 50,000. It has to be divided in half and also fenced in. Okay, the most efficient way to enclose the area is to construct the fencing so that the total length of the fencing is minimized. Alright, if the length of the field is 20, what's the width? Well, length times width equals 50,000. Okay, so if the length is 200, the width is going to be 50,000 divided by 200, which is 250 meters. Okay, B, find an expression for the width in terms of the length. Okay, well, we'll just do the same thing we just did here, right? Width equals 50,000 divided by 200. You can just say width equals 50,000 divided by L. All right, next, write down an expression for the total length of fencing. I guess I'll call that F. Can't use L. Total length of fencing, well, this is L and this is a W, so that's going to be 3W plus 2L. All right, and we already have this solved for W, so you can actually just substitute that into here, because you want one variable. We want one variable so that we can well, either graph it or do some calculus with it. So that's 150,000 over L, or let me write that as 150,000 L to the power negative 1 plus 2L. Okay, in part D, use your expressions to determine the dimensions needed to make it a minimum. Okay, that involves the derivative. So we can say df dl, the derivative, equals negative 150,000 over L squared. Or let me just rewrite that. L to the power negative 2, and this is plus 2. Okay, now how do we use the derivative to find the minimum? We set it equal to 0. Set it at the minimums and maximums, the derivative equals 0. So this is negative 150,000 over L squared plus 2. So I can bring this to the other side. 150,000 over L squared equals 2. 150,000 equals 2L squared. So L squared equals, if I do 150,000 divided by 2, we get 75,000. Okay, so then let's square root that to get the length. Okay, square root 75,000, 274. 274 meters, and to get the width, it's just 50,000 divided by the length. Oops. So we can click and copy and paste the exact value. It's 183. Okay, so this gives you the optimal fence length. Okay. Now there's a bit of a typo on the next one. Let me put in a 2 here. Okay, a metal container is the shape of a square-based cuboid. Okay, so let's draw a square-based cuboid, also called a rectangular prism. Okay, here it is. This is x, x, y. And they give us the volume, so that's what you start with. Volume equals x times y. And they give it to us, so that's 27. And we're going to have to show that the area equals this. You always end up solving one variable. So I'm going to just divide by x squared. So we have y equals 27 over x squared. And let's start with the area formula. The area, well, there's 6 sides on a cuboid, 6 faces. 2 of them are x squared, so 2x squared, plus 4 of them are xy. Then you see you just take this expression and substitute it for y. So we get 2x squared plus 4x times 27 over x squared. 2x squared plus 108. That's going to cancel, give you an x to the power negative 1. Yeah, let's write x to the power negative 1. It's going to give x to the power 1 in the denominator, which is x to the power negative 1. Part B, find the derivative. So that's going to be 4x reduced exponent by 1. That's going to be negative 108 x power negative 2. Or 4x minus 108 over x squared if you wish. Hence, so you have to use the derivative. Find the height of the container, which minimizes the surface area. So set the derivative equal to 0 and solve that. Okay. Okay, we can type that in to solve it. We can type in 4x minus, let's do a fraction, 108 divided by x, divided by x squared. Okay, so let's just plot. Okay, so it's kind of zoomed up. You can see this one x-intercept right there. Menu function root is 3. So x equals 3. You can draw a simple picture if you want to show what you did. But the question asks you for the height of the container. Okay, so if you want the height of the container, we have to we have y equals 27 over x squared, so we'll use that. 27 over 3 squared, so y also equals 3. Okay. So actually, this would be, in this case, x is 3 and y is 3. It would actually be a cube. A cube minimizes the surface area.